We are living in a very narrow window of time. One of those rare moments in history where the future hasn't just arrived quietly. It's accelerating toward us. Faster than laws can adapt. Faster than institutions can react. Faster than most people realize. For the first time, humanity is not just building better tools. We are building something that can think, reason, and eventually outperform us at almost everything. Artificial intelligence is no longer a science fiction concept. It's not a future problem. It's here, and it's improving at a rate that even its creators find surprising. At the same time, the world is entering a new kind of competition, not one defined by land or oil or even weapons, but by intelligence itself. Nations are racing to lead, knowing that whoever solves this first doesn't just win economically, they shape the rules of the future. And while this is happening, the nature of work, the thing most people trade their time for, is beginning to dissolve. Jobs that once felt permanent are becoming optional. Skills that took decades to master are being learned by machines in days. This forces a very uncomfortable question. If machines can do everything better, what is left for humans? Yet, this isn't a story of collapse. It's a story of transition. Energy, for example, is moving from scarcity to abundance. Clean power, storage, and electrification are unlocking a world where growth no longer means destruction, where progress doesn't require burning the future to fuel the present. And then there are robots, not behind factory cages, but walking among us. Machines designed in our image, capable of doing the tasks we don't want to do, shouldn't do, or simply don't need to do anymore. This moment can lead to extraordinary prosperity or extraordinary risk. The outcome isn't guaranteed. It depends on awareness, preparation, and the decisions we make right now. Because the future isn't something that happens to us. It's something we build. Artificial general intelligence is approaching at a speed that most of society is deeply unprepared for, not because people lack intelligence or intent, but because exponential change is fundamentally difficult for the human mind to grasp. For decades, technological progress felt linear. Computers got a little faster, software improved gradually, and automation affected only narrow tasks. That mental model no longer applies. Once intelligence itself becomes a technology, progress compounds. Each improvement helps design the next improvement, and the curve stops looking like a straight line and starts looking like a vertical wall. What makes AGI different from every previous invention is not just capability, but generality. Previous machines were tools that performed specific tasks under human direction. AGI, by contrast, is designed to understand, reason, and adapt across domains the way a human can, but without human limitations like fatigue, emotional bias, or slow learning cycles. This means the moment it crosses a certain threshold, its usefulness and influence expand dramatically, and the timeline from impressive to dominant becomes very short. Society tends to react to visible disruption rather than invisible acceleration. By the time AGI's impact becomes obvious to the average person, it may already be deeply embedded in critical systems, finance, infrastructure, research, defense, and governance. At that point, slowing it down becomes extremely difficult, not only because of competition between companies and nations, but because of dependency. Once systems rely on advanced intelligence to function efficiently, turning it off feels impossible. Another reason unpreparedness is so dangerous is that social, legal, and ethical systems move slowly by design. Laws are reactive. Education systems take decades to adapt. Cultural norms change across generations. AGI development, however, is moving on the timescale of months. This creates a widening gap between technological capability and societal readiness. The risk is not necessarily malicious intent, but misalignment, systems doing exactly what they are designed to do, in ways that conflict with human values or long-term stability. There is also a psychological dimension to this unpreparedness. People assume intelligence implies alignment, empathy, or shared goals. In reality, intelligence only optimizes objectives. It does not choose them. If those objectives are poorly defined, incomplete, or optimized without human context, the results can be harmful even without hostility. The more capable the system, the more amplified the consequences of small errors in design or intent. Ultimately, the challenge is not whether AGI will arrive, but whether humanity can mature fast enough to coexist with something smarter than itself. Preparation requires global cooperation, transparency, and restraint, qualities that are historically rare during periods of rapid technological advantage. Without deliberate effort, the speed of AGI's arrival may outpace our ability to guide it responsibly, leaving society reacting to outcomes it no longer fully controls. The global balance of power is no longer defined primarily by military size, natural resources, or population alone, but by the ability to develop and deploy artificial intelligence at scale. Intelligence has become a strategic resource, and nations that master it gain advantages that cascade across every sector, from economic productivity to national security. This shift represents a fundamental change in how power is accumulated and maintained, because AI does not merely enhance existing systems. It reshapes them from the inside. What makes this transition especially significant is the winner-take-most nature of advanced AI. Unlike traditional industries where leadership can be shared, breakthroughs in general-purpose intelligence create compounding advantages. The country that leads gains faster scientific discovery, superior logistics, better decision-making, and more efficient governance. These advantages reinforce themselves, making it increasingly difficult for others to catch up. As a result, AI leadership is not just about prosperity, but about setting global norms, standards, and rules. In this environment, the competition between the United States and China has become the defining dynamic. One side benefits from open research culture, entrepreneurial ecosystems, and the ability to attract top global talent. The other benefits from centralized coordination, massive data access, and the ability to deploy technology rapidly at national scale. Each model has strengths, and each compensates for weaknesses in different ways, making the outcome uncertain rather than predetermined. The danger arises when speed becomes the dominant incentive. When leadership believes that falling behind in AI could threaten national survival or long-term influence, safety and alignment concerns risk being treated as obstacles rather than necessities. This dynamic mirrors historical arms races, where the fear of being second pushed competitors to act aggressively, often underestimating long-term consequences. In an AI race, however, the cost of mistakes is not limited to a single nation because advanced systems do not respect borders. Another critical aspect of this power shift is that it blurs the line between civilian and military capabilities. The same models that optimize supply chains, predict markets, or accelerate medical research can also be used for surveillance, cyber operations, autonomous weapons, and information control. This dual-use nature makes regulation and transparency extremely difficult, as nearly every advancement can be justified as economically or scientifically beneficial. Smaller nations are also affected by this shift. As AI becomes more central, geopolitical influence may concentrate around a few dominant players, reducing the autonomy of others. Countries that lack access to advanced models or infrastructure risk becoming dependent on foreign systems for critical functions, effectively outsourcing decision-making power. This creates a new form of digital dependence that is less visible than traditional colonialism, but potentially just as impactful. The real question, then, is not simply who wins the AI race, but whether the pursuit of dominance can be balanced with cooperation. Without shared frameworks for safety, transparency, and restraint, the struggle for AI supremacy risks destabilizing global order in ways that no single country, no matter how advanced, can fully control. The structure of work that modern society is built upon is beginning to fracture, not because people are becoming less capable, but because machines are becoming universally capable. For centuries, human labor has been the primary engine of economic value. Education systems, social status, and personal identity have been closely tied to what people do for a living. As intelligent systems take on cognitive tasks once thought to be uniquely human, this foundation starts to shift in ways that challenge long-held assumptions about purpose and contribution. Unlike previous waves of automation that replaced muscle or repetitive motion, advanced AI targets reasoning, pattern recognition, and decision-making. This means disruption is no longer limited to factory floors or routine clerical work. Professions that require years of training, law, finance, medicine, engineering, and creative fields, are now experiencing automation pressure. At first, AI acts as an assistant, increasing productivity and reducing friction. But as capability improves, the assistant gradually becomes the primary performer, leaving humans in a supervisory or optional role. This transition creates an uncomfortable mismatch between economic reality and social expectations. Society still assumes that most people will earn a living by selling their skills, yet the demand for human skill is shrinking relative to machine efficiency. When machines can perform tasks faster, cheaper, and with fewer errors, markets naturally favor them. The result is not mass unemployment overnight, but a slow erosion of job stability, bargaining power, and income security, particularly for roles that rely on predictable cognitive output. Beyond economics, there is a deeper psychological impact. Work has long provided structure, meaning, and a sense of worth. When participation in the labor market becomes optional or limited, people are forced to confront questions that were previously abstract. If productivity is no longer tied to survival, how does society define success, dignity, and fulfillment? This shift requires cultural adaptation, not just policy solutions. Some responses focus on redistribution mechanisms, such as providing a baseline income to decouple survival from employment. While this addresses material needs, it does not automatically solve the problem of meaning. Humans are not motivated solely by consumption. They seek contribution, mastery, and recognition. In a world where machines outperform humans in most economically valuable tasks, those motivations must find new outlets. Education will also need to transform. Instead of optimizing individuals for narrow job roles, it must emphasize adaptability, critical thinking, emotional intelligence, and creativity, areas where human experience still matters. However, even these domains may eventually be shared with advanced systems, reinforcing the idea that human value cannot be defined purely by comparative advantage against machines. The redefinition of work ultimately forces society to separate human worth from economic output. This is a profound shift because it challenges a deeply ingrained belief that productivity equals value. Navigating this transition successfully requires intentional design of social systems, cultural narratives, and institutions that recognize humans not as tools in an economic machine, but as ends in themselves, capable of meaning beyond employment. The transition to clean energy is no longer driven by ideology or environmental idealism, but by basic physics, economics, and long-term survival. Industrial civilization has been built on the assumption that energy can be extracted, burned, and discarded without permanent consequence. That assumption is breaking down. Climate instability, resource depletion, and pollution are not abstract future risks. They are cumulative outcomes of an energy system that was never designed for global scale or longevity. Clean energy represents a structural shift rather than a simple replacement of fuel sources. Solar, wind, and other renewable technologies fundamentally change how energy is produced and distributed. Instead of relying on centralized extraction and combustion, they convert naturally abundant flows into electricity with minimal ongoing cost. Once infrastructure is built, the marginal cost of energy approaches zero, creating a pathway toward abundance rather than scarcity. This economic reality is increasingly difficult to ignore as renewable technologies continue to decline in cost while fossil fuels become more expensive to extract and manage. Energy storage is the critical enabler of this transition. Renewable sources are intermittent by nature, but advances in battery technology allow energy to be stored, transported, and deployed on demand. This transforms electricity from a fragile, moment-by-moment commodity into a stable, scalable resource. When combined with electrification of transportation, heating, and industry, clean energy becomes a comprehensive system rather than a niche solution. The result is a more resilient infrastructure that is less vulnerable to geopolitical shocks, supply disruptions, and price volatility. From a strategic perspective, clean energy reduces dependence on finite resources and unstable supply chains. Nations that invest early gain energy independence, improved security, and greater control over their economic future. This has implications beyond environmental outcomes. Energy abundance lowers the cost of manufacturing, computing, and automation, amplifying progress across nearly every sector. In a world increasingly driven by data centers, AI systems, and electrified infrastructure, access to cheap, reliable power becomes a competitive advantage. There is also a moral dimension to the shift. Fossil fuel combustion externalizes harm, transferring costs to future generations and vulnerable populations. Clean energy internalizes responsibility by minimizing long-term damage and aligning economic incentives with sustainability. This alignment makes large-scale adoption more feasible because it does not rely on sacrifice, but on superior performance and cost efficiency. The urgency of the transition lies in timing rather than feasibility. The technology exists, and the economics are increasingly favorable, but infrastructure and policy decisions operate on long timelines. Delays compound risk, locking in emissions and climate effects that persist for decades. Treating clean energy as optional or incremental underestimates the scale of transformation required. It is not an alternative path running alongside the old system, but a necessary foundation for any future that intends to sustain advanced civilization without eroding the conditions that make it possible. The transition to clean energy is no longer a matter of preference or environmental branding, but a requirement imposed by reality. Modern civilization depends on vast amounts of energy, and the methods used to generate that energy determine whether progress is sustainable or self-destructive. Fossil fuels enabled rapid industrial growth, but they were never a long-term solution. They extract value accumulated over millions of years and release consequences that persist for centuries, creating an imbalance that compounds over time. Clean energy changes the equation because it aligns human progress with natural systems rather than working against them. Solar, wind, and other renewable sources draw from flows that are continuously replenished, making them fundamentally scalable. Once the infrastructure is built, the cost of producing energy drops dramatically, shifting economies from scarcity-based models to abundance-based ones. This has profound implications, because energy is the input behind nearly everything: manufacturing, transportation, computation, food production, and even information flow. The real breakthrough comes when clean generation is paired with large-scale energy storage. Batteries transform intermittent power into reliable infrastructure, allowing electricity to be available when and where it is needed. This reliability makes it possible to electrify sectors that were previously dependent on combustion, such as vehicles, industrial processes, and heating. As electrification expands, efficiency increases because electric systems waste far less energy than combustion-based ones. The result is not just cleaner power, but a more optimized civilization. There is also a strategic dimension that often goes overlooked. Energy independence reduces geopolitical vulnerability. Countries that rely on imported fossil fuels expose themselves to supply shocks, political pressure, and conflict. Clean energy, by contrast, is locally produced and widely distributed. This decentralization makes systems more resilient and less susceptible to disruption. In a world facing increasing instability, resilience becomes as valuable as raw capacity. Economically, clean energy accelerates technological progress. Cheap, abundant electricity lowers the cost of computation, automation, and artificial intelligence. Data centers, robotics, and advanced manufacturing all scale more efficiently when energy constraints are removed. This creates a feedback loop where clean energy enables advanced technology, and advanced technology further improves energy efficiency and storage. The moral argument is inseparable from the practical one. Continuing to burn fossil fuels shifts risk onto future generations without their consent. Clean energy represents a commitment to long-term thinking, where economic growth does not depend on degrading the systems that support life. It is not about limiting progress, but about redefining progress so it can continue indefinitely. The challenge is not whether clean energy can support modern civilization, but whether society can transition fast enough to avoid locking in irreversible damage. Infrastructure decisions made today shape outcomes for decades. Treating clean energy as optional underestimates its role as the foundation for any stable, technologically advanced future capable of supporting both innovation and survival. Humanoid robots represent a shift in technology that goes beyond automation and enters the realm of physical intelligence integrated into everyday life. Unlike specialized machines designed for single tasks, humanoid robots are built to operate in environments designed for humans. They can use the same tools, navigate the same spaces, and perform a wide range of activities without requiring the world to be redesigned around them. This generality makes them uniquely powerful because it allows one platform to replace or assist labor across countless domains. The economic implications are profound. Labor has always been a limiting factor in production, constrained by availability, cost, and human endurance. Humanoid robots remove many of these constraints. They can work continuously, scale rapidly through replication, and improve through software updates rather than retraining. As their cost declines and capability increases, the price of physical labor trends toward zero. This fundamentally alters economic models built on wages, productivity, and scarcity of work. Initially, humanoid robots will be deployed where labor is dangerous, repetitive, or undesirable. Manufacturing, logistics, construction, mining, and disaster response are natural entry points. Over time, as reliability and dexterity improve, they expand into service roles such as caregiving, maintenance, and household assistance. Tasks that once required human presence become optional, not because humans are incapable, but because machines can perform them with greater consistency and lower risk. This transition reshapes not only industries, but social structures. When physical labor is no longer a primary source of income for large portions of the population, societies must decouple survival from employment. Wealth creation shifts toward ownership of systems rather than participation in tasks. Without thoughtful design, this concentration of productive capacity risks widening inequality, as those who control robotic infrastructure gain disproportionate advantage. At the same time, humanoid robots create the possibility of unprecedented abundance. Goods and services that were once expensive due to labor costs become widely accessible. Construction becomes faster and cheaper. Care for aging populations becomes scalable. Infrastructure maintenance improves in quality and consistency. These benefits, if distributed effectively, can raise baseline living standards across society. There is also a psychological and cultural adjustment required. Humans have historically defined themselves by what they do with their hands and bodies. When machines take over physical tasks, identity must shift away from labor as a measure of worth. Creativity, relationships, exploration, and personal growth become more central, but this transition is not automatic. It requires new narratives about value and contribution. The coexistence of humans and humanoid robots will depend on trust, safety, and alignment. Machines operating in close proximity must be reliable and predictable. Errors in physical systems have immediate consequences, making robustness essential. As robots become more capable, clear boundaries and oversight are necessary to ensure they remain tools that serve human goals rather than systems that optimize purely for efficiency. Ultimately, humanoid robots force society to confront a fundamental question. If machines can do nearly all physical work, what should humans do with the time and freedom that remain? The answer will shape culture, economics, and purpose in the decades ahead, determining whether this technological leap leads to widespread flourishing or deep structural imbalance.